In this video, we'll dive into the wonderful world of WebAssembly with the Go language. A brief introduction on WebAssembly, or WASM if you haven't used it before. It's an assembly-like bytecode format that an interpreter can execute as native code, comparative with .NET assembly DLLs. The difference is that WASM is intended for a secure context, like a web page, and is supported by a large variety of language compilers, such as C, C++, Rust, and notably Go. Essentially, it's intended to make the web platform support more than just JavaScript, to use the performance, ecosystem, or other advantages of other languages for web pages. As mentioned, the Go compiler supports compiling to WebAssembly and provides a handy set of imports, exports, and a runtime script, allowing you to easily interact with JavaScript APIs from within Go code. Let's use this to create a 3D application. The application is simple. It renders a cube with a skybox background and rotates the camera around it. It uses WebGPU, but let's not get into the details of WebGPU. All you need to know is that it's a GPU API for both graphics and compute, and we are using it only for graphics here. WebGPU is quite a complex topic of its own, so maybe in another video. At the bottom, we have an FPS counter to measure performance. To simulate a low-end machine, we can go to the developer tools and throttle the CPU execution. We will set it to 6 times slower. Even with this, the FPS matches the refresh rate of our monitor, so everything's running smoothly. Now let's render 10,000 cubes. The frame rate dropped, which was kind of an expected result. Now let's test the exact same application but with JavaScript instead. And it's completely smooth. What's going on here? How is JavaScript faster than Go? To understand this, let's dive deeper into how WebAssembly works with the standard Go.js interface. The WASM standard itself can only expose functions as interfaces between the host and the module. The host exposes functions to the module via imports, and the module exposes functions to the host via exports. Import and export functions only support parameters and return values with scalar values, that is, integers and floats. This makes the interface very limited, as you cannot pass structures or strings directly with this interface. However, both the host and the module can read and write memory assigned to the WASM module. This linear segment of memory can be used to pass more complex data between host and module, provided it is serialized in a format that both sides can understand. The Go interface adds an abstraction layer here which allows you to use JS values directly in Go. The objects do not actually exist in Go memory. The values are merely numeric identifiers which map to a JS object in JS memory, managed by the Go.js runtime. Whenever we want to create JS objects, the data is serialized to JSON and then parsed by the runtime to create the object. So if we look at our rendering code, we are using the Go.js interface heavily, and each use includes serialization, deserialization, and object lookups. And this is done for 10,000 cubes on every frame. Needless to say, that adds up and is not acceptable for a high-performance application. So, how do we fix this? The optimization is rather obvious. Reduce the amount of JS calls during the render function. Instead of passing each individual WebGPU command as a separate call, we can batch together commands and send them to JS via a single call. We could serialize in the JSON array, but JSON is not a very optimal serialization format, so we'll use a simpler binary serialization. Our application makes its own linear memory space, and we can then use that to write our binary data. Then in JavaScript we use data views to read this memory region. Another optimization we'll do is pre-calculate and write the uniform buffer for each cube, as they do not change their positions. Now, with these changes, we are getting a smooth frame rate, just like in the JS version. This is a very important thing to understand if you are writing applications with WebAssembly. There are costs to using the WASM.js bridge, and that cost depends on how complex data structures are handled. If this 3D rendering was part of a larger application, I would still stick with the Go.js interface, as that is easy to use for less demanding use cases. But since we are mostly interested with rendering, we would ideally not use the Go.js interface and switch to something more bare bones. And that something is WASI, or WebAssembly System Interface. WASI is a standardized set of imports for WebAssembly modules that provide basic operating system interfaces, such as working with files and sockets or generating random data. Go supports compiling to WASM Preview version 2 using the WASM 2 as the Go OS environment instead of JS. This removes the dependency for the Go.js runtime, but it also removes features supported by the runtime, such as the aforementioned JS values and also support for Go routines. But for this project, that is okay, since we don't need them. We actually don't need WASM either, but there is no support for Go for compiling a bare-bones WebAssembly module, so that's the minimum we'll have to work with. However, the WASM interface can be implemented with mostly stub implementations in just a few lines of code. So, to summarize, minimize crossing the host module bridge and use efficient serialization for passing data. This is important for any WebAssembly module written in any language. Go just has a rather inefficient method by default, but as you can see, it can be improved. That's all for this video. Thanks for watching. Bye.